This is the NASA's James Webb Space Telescope Town Hall. We are going to do a lot of different status updates, user committee updates, and user tool information. You are also going to get the chance to learn about the early release science programs and meet some of the PIs and team members for those. So we're going to go ahead and kick this off now. I'm going to give you guys a little bit of an agenda overview. I mentioned in a few minutes Eric Smith's going to come up here and talk about the status of JWST. Then we will have James Bullock, the head of the user committee, come talk. Then Ken Sembach will introduce the early release science PIs, after which, and this is the interesting thing, there's going to be teams of ERS team members come up, and they will introduce their programs to you as a group. So you'll hear from two or three at a time, and after that, you're going to get 5 minutes to ask them questions. So I'll help moderate that a little bit, but be prepared. We have microphones down the center aisle. Raise your hand if you need assistance and we can bring one over to you. And that way you can stay for the things that you find interesting, that you want to ask those PIs when you have the question fresh in your mind. So be ready for that. And then after that, we will go into our user ecosystem, all the tools and help that we have available for you as JWST users. Okay. And then afterwards, we're going to have a dedicated time, open mic, for your questions that you didn't get to ask before. Now I'd like to introduce Dr. Eric Smith to give us a status update on the James Webb Space Telescope.
Okay, well, thanks everyone for coming out to the town hall tonight. As you saw from what Bonnie said, it's going to be focused mainly on you guys, the user community now, which is appropriate for the phase of the mission we're at. But I just want to review with you what was a very significant year for us on Webb. We're now down to pretty much just two big pieces of hardware. The first is the science payload itself. You'll hear us refer to that as OTIS, which is that combined acronym of the telescope and the science instruments. Talk about the testing that it went through this year. And the other main piece, of course, is the spacecraft bus and the SUNSHIELD, which is now we call the spacecraft element. Of course, these two pieces of hardware need a lot of software and ground systems to make them work. There was a lot of progress along there. And for the first time, we'll also hear about progress in the science front when the ERS folks come up and give their talk. So to take us back to the beginning of this past year, we had the OTIS at Goddard, where it was finishing up its environmental testing. Environmental testing is when, after it's been all put together, we vibrate it and we blast it with sound in a similar fashion that it would experience when it rides the Ariane 5 into space. There you see it going in the acoustic chamber. Now it has come out of the chamber, and this is significant because we've now given the science payload the same sort of effects it would see on the way up to space. So we take it now down to the Johnson Space Center, and now we're going to put it in the space-like environment. So can it survive the stresses of launch that it will see and function as appropriately? Here you see the transportation system we use. This is the 5-mile-an-hour trip down the Beltway, so it's only half the normal speed on the Beltway. And here is the C5 transport plane, and you can see we just fit inside the largest transport plane. Here it is now arriving down at Johnson. And once they take it here, they'll put it into a clean room. Oh, you have to sometimes move traffic lights because the structure is so large. And so we see them doing that. Here they're rolling it into the clean room, which is just outside the chamber. This was occurring during the late spring as we were prepping it to go in for the test. And so here it's going on a rollover fixture there. And so that's a very nice video put together by the folks at Goddard. And there are many more of these, actually, if you go on the Goddard website, and they're all downloadable there from the YouTube link. So it sat in this chamber for 100 days, and here you can see a reading from the temperature inside the chamber and outside in Houston. And so for 100 days, this is what you saw when you looked at the webcams. And then at the end of those 100 days, we took it out. Those helium shrouds were, moved to the side. Built the shortest railroad in Texas to pull it out. And then we end with this shot, which was a press release. These are all the technicians that helped with the test down there, and that's a beautiful shot by Chris Gunn, who took that photo. So what did we learn out of this test? Well, many things, but 4 really important things for the group here. And the first and most critical is probably the fact that we verified the performance after a launch. So put it through the launch stresses, put it in the environment it's going to see, and things worked as planned. So that's a huge verification in the test. The alignment of the whole optic system. This is the first time we had all the instruments and telescope together working in a cryo environment, and they worked as planned. Critically for the science, we affirmed that we can make these 18 segments work like a single mirror to the diffraction limit of 2 microns. And then perhaps a little more subtle but important for Webb is that we confirmed the thermal models that we use for the telescope, so we understand how it's going to behave, because we never get to test the whole system in a similar cryo vacuum. It's too big to fit into any chamber in the world, and so we rely on our ability to model it, and the test at Johnson helped confirm that our models are good. And actually, before we move on to that, can I just get a quick show of hands of people who were in this room who participated in that test down at Johnson? Okay. Everybody who's not raising their hands in here needs to give those people a round of applause. They did a test that was been under planning for about 2 decades, was thought to be the biggest tall pole technologically, integration-wise in the program, and they did it during a hurricane. They kept working straight through it, so they did a tremendous job, and I can't really thank them enough because they did something amazing. The other big piece that I mentioned was the spacecraft and SUNSHIELD, and so there's going to be a little video. I think some of you may have seen this. Paul Hertz showed this. The video depicts about 15 months of activity in 3 minutes, and it starts out at the clean room. This is in Northrop Grumman now in Southern California, and they'll be bringing the spacecraft bus into a stand, and so it's this black cube. I'll try to narrate it. Is there a laser pointer here? I don't see one there. Then their various components are going to be integrated into this, and then it ends with the fully deployed SUNSHIELD. Now, of course, the other thing that happened this year is that we did have to move the launch date, and that was primarily a result of activities along this line of the hardware integration and test that we either had issues with, such as in the propulsion system. There were a couple of things that we had to redo in the propulsion system, and then just the pace of work in this integration resulted in things taking a little longer, and so to have adequate margin to a launch date, we needed to move it out. And we had to tell ESA when we wanted that launch date right around September of this year, and so that's when the announcement came out after we realized we needed this extra activity. And so we'll just start here. So you'll see the spacecraft bus is right here. And there they'll put it on this stand where they'll begin all the integration activities. The cryo cooler going in. You can start to see some of the avionics, the electronics here. There's the core of the SUNSHIELD. One of the other things I want you to take note of, is how many of this is when they're getting ready to do electrical testing, isolation structures there. the number of people in the room at any one time, and the number of times they have to do activities on the so-called diving boards. These structures, this is a very complex integration task. Here you see the pallets that will hold the sun shields being integrated. Here are the booms that will pull it out. This is a telescope mass simulator. These are tables that they use to lay out the sun shield on. Here they'll assemble the other tables over here. Then they'll actually bring out the membranes. The membranes aren't installed yet. Here's a membrane that's going to be installed on there. And then you'll see them stretch out. Presumably this is layer 1 here they put on. And then a couple other layers will go on there. So this is now the flight hardware. Of course, we did this with an engineering model, but the deployment you're going to see is now a deployment that was done with the avionics. Previous deployments were done more or less manually, by hand, as it were. And so when they actually do the deployment, you'll see here it's being driven by the spacecraft electronics. Before they do that, however, now you see this is the cover over the membranes. That's why it's pinkish. It's a different coating on the material. They'll put the telescope mass simulator back on it, and they'll do the modal testing on it. Take it out and hit it with a hammer. Again, just note the amount of activity, the amount of people in the room for each one of these steps. So you got people doing the web, you got safety people there, you got contamination people out there. And this is roughly then the launch configuration that everything will be in. And so that's when you want to, this is how it will be tested subsequently for its environmental test. So it's a popular test. A lot of people here working on that. And at the end of this, when we're all done tonight, there are a number of folks here from Northrop Grumman, so if you have detailed questions about the SUNSHIELD deployment or the spacecraft element, we can certainly hook you up with those folks to talk about them. And so now we'll get ready to do the deployment. Here is the core, so that concertina type structure fans out, creates a separation near the center of the observatory. And then once the layers are out, they're tensioned to get the separation needed so we can get rid of the heat out the sides of the sun shield. And then it will end with it fully deployed. Now, if you were to go out to this clean room in California now, you'd see things are folded back up. They're getting ready to do the next step, which is what we'll talk about on the next slide. What's left for the hardware? So on the science payload side, the OTIS side, we're going to be shipping it out to Northrop Grumman around the end of this month. The exact date depends on the availability of one of those Air Force C-5 planes. Then we'll do some deployment tests of the OTIS, the secondary mirror tower, and the aft deployable radiator when it's out there. On the spacecraft element side, one of the things we needed to do, sort of, again, help put that delay pulse in, was we needed to replace some thrusters that were leaking, and so all the components for those thrusters have come to Northrop Grumman. They're being reassembled now, and then next month we should start the reinstallation of that. Once that's done, we will put this, the spacecraft element through its environmental testing, vibe, acoustics, and thermal vac. Do some deployment tests of it again to make sure that it survives the ride to space, as it were. At that point, these two pieces get integrated, and then it goes through a similar series of tests here. Of course, these are now all, many of these things have been done to the components, but it's now being done at the whole observatory level. So, there's lots of things that go on in each of these lines, so it's a very top level, but there's a finite number of tasks in front of the hardware. On the operations side, big year because we got to test the institute commanding the spacecraft, which sits out at Northrop. So it's a nice test of the ground system. That was passed the missions operation review, and the flight operations team are beginning exercises at the institute. If you haven't had a chance to go there and see the beautiful mission operations center, it's fully ready to go. And of course, as we'll hear later, we had this call for early release science. 100 some proposals were received, 13 of those were selected. And so about a year ago, I think I ended the presentation saying, you know, now it was your turn. Of course, I had no doubt that people would step up to the task, as they did, and it's really exciting after all this time to see what the telescope's really going to do once it's up there. One thing I'll point out on the next slide is all the work that the Institute has been doing trying to get the community prepared. So there have been numerous conferences, and there's a lot of what are so-called community lecture series that they hold at the Institute. I think all of these are online, if I'm not mistaken. So if you weren't able to go to any of these things, you can go to the Institute's website and get the lessons there. So I would encourage you to do that, because Webb is not a simple observatory to operate or observe with. And so it's great if you can take advantage of all the work that's been done to get folks ready. A couple of things on the programmatic side. So it's thrilling to put up a budget chart. Our budget has stayed the same since the replan. These are in millions of dollars, and so here you can see this is now in the operations phase. There's a little bit of sustaining engineering in that money there. For 7 years, we have gotten the budget from the administration. They have requested what we've needed. Congress has funded that for 6 years. We're under continuing resolution now, so hopefully they will give us that number there. That we don't have any doubt that there's no indication they don't want to give us that number. Just a matter of them finishing that up. We expect our what we hope to be the final GAO report. That was congressionally mandated later this year, probably in March. And then these are the big reviews that we have coming up. We've got a schedule review coming up at the end of this month, the system integration review, and this KDPD are formal NASA reviews that you do before you integrate the science payload with the spacecraft. And so those will happen before we do that integration in the summer. So as far as the status, we had a very successful year with the science payload. It passed its environmental testing. There's a few more T's to be crossed and I's dotted on the review of the test results, but basically it shows it can deliver the science that we have planned for all these years. This year, it's going to be a year for testing that spacecraft element and integrating it. And while we did have to move the launch date, I do want to point out that we are still within our replanned budget that we set out back in 2011. And I don't know if we want to take questions now or later, but at the end, okay. So, thank you.
All right, next on the agenda is the JWST Users Committee, or JSTUC, and is going to be presented by its chair, James Bullock.
Okay, thanks very much. It's a pleasure to be here. So several months ago, Ken Senbeck called me up and asked if I'd be able to chair the user committee for JWST. And I said, so you want me to chair a users committee for a telescope that nobody's using? And he said, yes. And I said, well, that sounds exactly like the kind of job I can handle. So that's why I'm here. But what are we really doing here? So just to let you know what we are, so we do expect James Webb to be in use starting sometime after 2019. And we're the committee that's appointed to sort of help interface with the user community and talk to the people at Space Telescope, the folks at Goddard, to sort of make sure everything is being used optimally. So we're providing user advice to the observatory as a whole, and we're also maximizing scientific performance. When we write reports that are presented to Ken Senbach and John Mather to sort of provide input in that regard. We have actually a lot of freedom, and with that, we're really asking for the community, so everyone here and people on the interwebs there, to help us figure out what it is we want to do and set our priorities. And so this is really the first open call to present ourselves to you to start having that kind of dialogue. There's a website that's presented here, and you can find it pretty easily if you just Google James Webb Space Telescope User Committee. This will pop up, and that's one way you can find out about who we are and how to reach us. Here's the list of people on the committee. I don't know if anyone who's on the user committee, or can you raise your hand? I don't know if anyone's here. Okay, a few of us are here, one or two. Anybody who's got their hand up, you can come talk to us directly, and I'll talk to you a little bit more later about how the best way to interface with us. Like I said, our email addresses are on the website. We've actually had our first meeting, which took place in September. And this was really a great opportunity for all of us to get together and learn about what's happening with James Webb. So we really, from top to bottom, we got a sort of overhaul on what's happening, what the timelines are, and what the needs are. And I have to say, it was an extremely impressive set of presentations. I mean, it's the A-team from top to bottom, from the folks at Space Telescope who are writing the software to the engineers who are building the telescope. I mean, all the way along, it's really just exceptional. It's amazing what's being done, and it's an honor to be a part of this, and we're super excited for this telescope to launch. We have had, so what we're going to be doing is issuing a few statements occasionally about sort of top priorities of the JSTUC, and what we've done so far is endorsed what's happening with the Cycle 1 call after some bit of discussion. As you all know, the launch date has slipped, and we may be looking at, for example, a June 2019 launch. And the Cycle 1 call, however, has already come out. But one way we're going to try to mitigate the sort of potential we're making sure that we're not going to lose science opportunities. We are endorsing the idea of having a mid-cycle call between Cycle 1 and Cycle 2 that will optimize science. And this supplemental call will come out sometime around the time of launch, we think. And what we're doing now is trying to figure out the nature of that call, how many hours are going to be allocated, and the best way to do that in a way that maximizes science return for the community. So I don't want to take up too much time here, because it's really a time for us to listen to you, but I want to tell you a little bit about what's on our radar and what we're sort of have our ears open for to try to get some feedback on. So really the supplemental call is high on our list, try to figure out recommendations for what we want to do with that supplemental call. How big is this allocation going to be? What fraction of the community feels like it will have new science targets that won't be available during Cycle 1 call, but would be available about the time of JWST launch? For example, if there's a bunch of new targets that come available because of tests, we want to know, well, roughly how much time are we talking about to meet that need? And we want to figure out how to write that call and use it in the best possible way. So this is sort of, we're open for this. We also want to make sure that we are hearing the users if there are ways that the user experience can be improved with, say, APT, ETC, and the JDocs, the documentation that's online. So, for example, if you put in, when you propose for ERS time, if you had significant difficulties, please let us know about that, and we're going to try to be a way to interface with ST and make sure those tools are being used, or are being set up and in a way that's most efficient. And finally, maybe even our highest priority right now is hearing from the community. And any ideas on the best way we can hear from you, we're going to try to fan out and attend as many of these meetings that Eric mentioned earlier as possible and make ourselves available. If you want to talk to us, like I said, we need to set up a better way of doing this. We're working on getting just a blaster email that you can just send to all of the JSTUC. You're welcome to contact me if you have questions or issues that you'd like to raise. All of us, our names are listed on the website, and you can contact us that way if there are people you know in your communities that you want to talk to. A few of us will be around at the JWST booth. So this is the Space Telescope booth, not the NASA JWST booth. We'll be available for the next couple nights. And so if you want to come by about 5:30 in the evening on Wednesday and Thursday, there'll be representatives from the JSTUC there if you just want to talk to us in person. And we're hoping to have more ideas in the future about the best way to interface with everybody. And that's it. So thanks very much.
Thanks, James. We're going to keep you busy. I'm Ken Sembach. I'm the director of the Space Telescope Science Institute. One of the nice things that I inherited when I became director 2 years ago was the responsibility of allocating some discretionary time to early release science programs that were going to address some of the fundamental topics that JWST is going to be investigating over its lifetime. And the purpose of this program is to provide an early look at what JWST is capable of. And by early, I mean within the first few months of the telescope's science operations. So these are observations that will be happening within 2 or 3 months of the commissioning of the observatory. All of the data are public immediately, so that gives everybody a chance to take a look at the data from a variety of programs that sample many of the different commonly used modes for the observatory. We issued the call earlier this year. As Eric said, there were 106 proposals submitted for almost 3,700 hours of observing time. And there were about 3,000 investigators or collaborators among those 106 proposals. So a large fraction of the community participating in those early release proposals. We selected 13 of them. We convened a peer review at the Institute over the summer. There were 31 scientists brought in to help me with that selection. They presented me with a set of very compelling programs. And from that, we selected 13 proposals for about 460 hours of observing time up front. And those 13 proposals have 250 some investigators from 18 different countries, 22 US states, and 106 unique institutions represented. So I think we've done well in covering a broad swath of the community. Many of those investigators are in the United States, but obviously many of them are also from overseas. The selection of those was difficult because essentially all of the proposals we received were very good. And for those of you who might have been associated with some of those proposals that weren't selected, I encourage you to submit them as Cycle 1 proposals because I think they'll be very competitive. This is a slide that shows the distribution, the approved and submitted percentages of those ERS proposals in different categories, stellar population, stellar physics, and so on. The blue bar indicates the submitted fraction relative to that total number of 106, and the red bar indicates the approved fraction relative to that number of 13. And as you can see, in most cases, the bars are about equal length. The one glaring exception there is cosmology, and it's not that we're not doing cosmology with this telescope in the early release science program, it's just that many of the cosmological types of investigations were classified under the galaxies and high redshift portion of this plot. So I think there's a good distribution in scientific categories as well. Similarly, there's a very good distribution in the different instrument modes that are being used. All 4 of the instruments and many of the different modes are being actively used by multiple proposals in some cases. And in many cases, individual proposals proposed observations that were being used by multiple instruments. One of the nice things about this is that we get not only a broad selection of information about the different capabilities of these modes, the ERS programs are specifically designed and were also selected based on the science-enabling products that the proposers suggested that they would produce in time for the Cycle 2 call for proposals. And that means that for each of these modes and for each of these proposals, the observers are going to be producing information that's specifically of use to you as a science community to help you understand better what it is that JWST is capable of at the time that Cycle 2 call comes out. You're going to hear about each of the individual programs next, so I'm not going to spend a lot of time on that. I'll just put up real quickly the 13 proposals that were selected just to kind of give you an introduction. I'll be around throughout the session here and happy to answer questions that you might have. I'll just finish by saying that I am delighted as the director of the Space Telescope Science Institute to be able to sponsor such a program, and the entire institute is at your disposal as a community to help you maximize the amount of science and the kinds of science that we get out of this fantastic observatory. We've been waiting as an astronomical community for a long time for this telescope, and it's coming quickly, and we're here to help you do your science. Thank you.
All right, so I promised that during these presentations, we're going to bring folks up in groups of 2 to 3. So we'll have the first group come up. These are roughly under the category of distant galaxies and cosmic dawn. Everybody will introduce themselves and tell you a little bit about their program in 3 minutes. And after each group, we'll have 5 minutes of questions. Okay.
Hi, well, my name is Mark Dickinson from NOAO, and I'm here on behalf of the Cosmic Evolution Early Release Science Survey, or SEERS, I think is how we're pronouncing it. The team is listed there, and our PI is Steve Finkelstein from the University of Texas at Austin. And the full SEERS team, including collaborators, is 105 people from institutions in 10 countries. So it's a big group of people, many of whom are excited, well, all of us are excited about the science, and many of whom are experienced with carrying out deep public surveys with Space Telescope and other observatories in the past. I want to thank Ken in particular for having the initiative to do this early release science program, which, of course, I mean, I'm excited because we're benefiting from it, but I think the whole community is really going to benefit from the early access to both JWST data and the knowledge that comes from executing these programs. Now, SEERS is a program to study galaxy formation and evolution at high redshift. Let's see, do we have a laser? Yes. It's focused on 1 to 5 micron spectroscopy and 1 to 20 micron imaging over areas that add up to 100 square arc minutes. It depends on the different instruments, suitable for investigation of galaxies at high redshifts out to as high as we can go. We're planning rapid reduction and release of our data products following the spirit of the Goods and Candles projects and others that we've been involved with in the past, with first catalogs released 6 months after data acquisition. And the primary technical goal, in a way, is to develop and validate strategies for deep field science observations using multiple JWST instruments in parallel. So we're using NIRCam with 5 to 6 filters of broadband imaging and slitless grism spectroscopy. NIRSPEC spectroscopy, primarily in the intermediate resolution mode, are of 1,000, but some low resolution are of 100, and MIRI imaging in up to 7 filters. We're going to be observing in a candles field, nominally in the extended growth strip field, EGS. I can't possibly walk through this figure, but once we have a website, you'll be able to study this figure in detail and see what our observing strategy is. But the point is that we're laying out parallel observations with multiple instruments in ways that we can study the same galaxies and the same fields in various ways, both imaging and spectroscopy at different wavelengths in order to understand high redshift galaxies and their evolution. Science areas, discovery of galaxies at redshifts greater than 10. Well, HST and Spitzer and other facilities have told us a lot about galaxies and their numbers out to redshifts of 8 or so, but only a little bit about galaxies at higher redshift. SEERS is designed to probe the higher redshift universe. Spectroscopic studies, something I'm particularly excited about, doing rest frame optical and ultraviolet spectroscopy of galaxies at high redshifts for diagnostic science. Galaxy morphologies in the rest frame optical to study the stellar structure of galaxies out to higher redshifts than we could do with HST, and high resolution and very sensitive mid-infrared observations with MIRI, both for just going deep and resolving galaxies that were previously unresolved, but also for studying with multiple filters their spectral energy distributions from strong mid-infrared features. These are just a variety of figures drawn from the proposal that I can't walk through that illustrate the science goals, but there are many that I just summarized before, and I hope that you'll be using the SEERS data to plan your Cycle 2 observations based on what the data products will be obtaining and releasing. Thank you.
Hi, my name is Jane Rigby, and I'm the principal investigator of the ERS program TEMPLATES, which stands for Targeting Extremely Magnified Panchromatic Lensed Arcs and Their Extended Star Formation. My co-PI is Joaquin Vieira. So templates, we are targeting 4 of the very brightest lensed galaxies that are known, for spanning a redshift range of 1 to 4. These are both very highly magnified galaxies and also very reasonably intrinsically bright, such that their apparent brightness is some of the brightest things on the sky at these redshifts. 2 of them are selected from the ultraviolet, so they have fairly low extinctions, and 2 of them are selected from the submillimeter, so they're very highly extincted. So in a small number of galaxies, we're trying to span parameter space for the redshift 1 to 4 universe. And I should say that the sizes of these galaxies are such that they're designed to fit in the integral field units of JWST. So we're using 4 science instruments, instrument modes. We're using mostly spectroscopy, IFU spectroscopy, integral field unit spectroscopy with NIRSpec, and integral field unit spectroscopy with MIRI, and then NIRCam and MIRI imaging as well. And so our primary data product are high-level maps of the rest frame optical emission lines, particularly H-alpha, maps of Paschen alpha, so that you can make extinction maps, maps of the PA features, maps of the spectral energy distributions. The spatial scales that we can probe with the help of gravitational lensing are about 100 parsec scales, so 30 Doradus size regions in the distant universe. And the main science goals are to measure the physical conditions of star formation and how much those conditions vary spatially in a way that you just can't measure without lensing, to demonstrate some of the extinction-robust star formation rate diagnostics that will be workhorses for JWST in the distant universe, to look at where the young stars are and compare that to where the older generations of stars have been, and really to resolve star formation and see what star formation looks like on 100 parsec scales. But even if you don't care about those science goals, these will be some of the best spectra of the brightest objects for integral field spectroscopy in the distant universe, and so you can use them to plan your Cycle 2 observations. And they have a large dynamic range, so you can see how well we do, signal to noise for not only bright things, but faint things as well. Thanks.
Okay, hi, I'm Charlotte Mason. I'm a co-I on the program GLASS, which is the GRISM Lens Amplified Survey from Space. And this program is combining the power of gravitational lensing with the power of JWST, targeting a massive cluster. So building on the legacy here of the frontier fields and our previous HST survey GLASS, we're going to be doing spectroscopy of hundreds of galaxies in this cluster field, enabling science from the epoch of reionization to the present day. So we're going to be looking at the cluster, the frontier field cluster, Able 2744, so I'm sure many of you are familiar with this cluster. There's a lot of data out there already, but now we're going to be able to use JWST's capabilities to study it at higher wavelength regimes. So our team has extensive experience in studying clusters with HST, with slitless spectroscopy and imaging. We're led by Tommaso Trejo at UCLA, and most of our team is in the University of California Space Telescope and the Rome Observatory. And the key goal, really, of GLASS is to use spectroscopy with JWST in the several different modes. So I think some of you will have had questions about, if I want to use JWST, which spectroscopic mode do I want for my science goal? And we hope to be able to answer those questions. So we're going to be using both NIRIS and NIRSpec on many of the same targets. So you're going to be able to evaluate which modes are best for your science. So in particular, we're going to be using NIRIS in the wide field slitless spectroscopic mode at low resolution, and then going to be using NIRSpec using multi-object spectroscopy at medium resolution. In both of those, we're going to be covering a wavelength range of about 1 to 3 microns. And the aim is to reach depths of about flux limits of about 2 times 10 to the minus 18 CGS. So this should open up a really broad range of unexplored territory in the spectra of high redshift galaxies. And then in parallel, we're going to be doing near-cam imaging. This will be in 2 fields. And here we're really looking to go to magnitude limits of about 29 point source magnitude limit. In terms of the products that we're going to be developing for the community, obviously as well as spectroscopic and imaging catalogs, one of the things we're going to be able to provide you with are some tools for exploring the spectra that we get out of GLASS. So in particular, graphical user interfaces for exploring the NIRIS and NIRSpec spectra, which we'll be able to release for you to use for Cycle 2 proposals. We're also going to be developing, producing spectroscopic templates of these high redshift galaxies. We don't know what their spectra look like in the rest-frame optical. Hopefully after this program, we'll be able to provide you with templates for these galaxies to inform your Cycle 2 proposals. And later on, we'll be able to provide a much more quantitative comparison of the NIRIS and NIRSpec spectra, which should help you inform Cycle 3 proposals, and you'll be able to use that to interpret the Cycle 2 and Cycle 1 data as well. If you want to know more, we have more information on our website as well, which is glass.astro.ucla.edu/ERS. Thank you.
All right. If anyone has any questions for these 3, please come to the microphone or raise your hand and we can try to get a microphone to you.
My name is Chris. I used to be an APT developer. I heard a lot of parallel observations. This is coordinated parallel at the same time. That's amazing.
It will be. And thanks to you.
Hi, KBL Space Telescope. What advice would you give to people who are thinking about putting in a Cycle 1 GO proposal, in particular for things like when should they start proposing?
Now?
Well, we started when we started writing this, but no, I mean, it's a complicated observatory, no question about it, and ST has done a wonderful job providing information, but even just learning where to find everything and digging through it takes time. So, and it's all new, right? I mean, many of us who've been writing HST proposals, kind of got the hang of it after a while. It's going to take some time with JWST, but it's certainly doable. I mean, so just ask questions. Asking questions is the key. And I mean, hopefully, I think these ERS teams, if we do our job, we'll be sort of maybe not much before the Cycle 1 deadline, frankly, because it's coming awfully soon, but certainly before the Cycle 2 deadline, will have gained enough experience, and that, you know, you should be asking us questions too.
I think just one thing to add is that I think a lot of the teams, we're stressing cookbooks, we're stressing getting out literature on what we did and why we made the decisions we did, and to get that out to the community.
You guys have 2 more minutes if anybody has questions. Okay, I don't see anybody moving toward the mic, so, oh, there you go, yay.
I am actually a scientist. I'm a Japanese public TV coverage, okay? And they transmit a program based on the result of JWST science, and I'm wondering when you plan to have the first results from your research available to the public that we can obtain to the public.
Well, it depends when the telescope is launched. But I mean, the data will all be public as soon as it's taken, basically, and it should be taken within the first 5-6 months of launch, or after commissioning.
Yeah, just to be more precise about that, and somebody who actually works at the institute to say this, but I mean, it's the commissioning period is like 6 months, right? So, and then the observations start. So if launch is June, you know, it's then, you know, observations will kind of start November, December, and then, you know, so we hope early 2020 we'll start to see the first, you know, it'll take a while before published results come out, but, you know, hopefully there will be people moving quickly to get the exciting science out in early to mid 2020.
Okay, are you, okay.
What is the status of the instrument pipelines?
Yeah. The status of the instrument pipelines?
And what state of maturity are there? So when the data comes out, how much, how useful are they going to be?
Okay. All right. I'll swap hats. Put on my project science hat. So we're writing the pipelines to be ready to grab the data. The pipelines already now can deal with the test data that we've taken from the cryogenic vacuum test that Eric spoke about. So the data will be ready. The very first data will have to use ground-based calibrations because we won't have taken the calibrations in space. And then we'll start replacing those ground-based calibrations with the calibration files taken in orbit. But the pipeline will be ready, and then you just plug in your data, plug in the calibration files, and then, as always happens, it's a question of tuning the parameters to deal with the on-orbit, you know, how the data actually look on orbit.
Sure.
Again, one of the jobs of these ERS teams is to be early guinea pigs and find out what works, what doesn't work, and then to work with people at STSCI to, you know, pass that experience back. I mean, there'll be other users, of course, the guaranteed time observers, and who are, you know, in many ways the definitive experts on these instruments. But we're the canaries in the coal mine for the general user community. It's what? And Jane asked me to say that it's an open source pipeline.
Thanks, guys. All right. We're out of question time for that one, so we're moving on to nearby and resolved galaxies. And we have 4 presenters in this one. I'll pass it off to you.
All right, so this is the Resolved Stellar Populations Early Release Science Program, and the PI is actually Dan Weisz, based at Berkeley, but he couldn't be here today, so I am Martha Boyer. I'm one of the lead co-Is. I'm based at Space Telescope. And so the overall goal of this program is to establish JWST as the premier observatory for resolved stellar population science. And it's really going to pick up where HST left off, because HST really transformed our understanding of the local universe through resolved stellar populations. But with Webb, we'll actually be able to do better. We'll be able to go deeper, we'll have more angular resolution, and we'll be able to do a lot more. And so we're focusing on a number of different science themes, particularly star formation histories and how you estimate these from color magnitude diagrams in the near infrared, and also the subsolar stellar IMF, because with JWST we'll actually be able to get to lower stellar masses than we could with Webb. We'll also be investigating proper motions, in particular in tandem with Hubble data that was taken very early on, so we have a very long baseline. And with that, we'll be able to actually do better than Gaia can do for some of these very distant systems. And then we'll also be studying things like evolved stars, embedded star formation. We'll be mapping ISM dust using extinction, and a number of other science goals. And down in the lower right is a near-infrared color magnitude diagram showing all the different features that you'll see in the near-infrared. And this program is going to basically sample this whole entire space that we're showing here. And just to illustrate what Webb is going to be able to do, the top of that diagram, where the tip of the red giant branch is marked along with AGB stars, we'll be able to do that with Webb out to 10 megaparsecs. And then as you go down into the main sequence turnoff, where you can study things like ancient star formation histories, you can do that out to 2 to 3 megaparsecs. And then if you go even deeper than what's shown in this diagram, you can see things like the main sequence kink in the near infrared, and you can do that out to something like 300 to 500 kiloparsecs. So for all of the, or for many of the ultra-faint dwarf galaxies, for example. And this particular program is going to sample this entire diagram. And along with the science that we'll be delivering, we're also going to focus on a couple of different products. Our primary product is to develop a PSF fitting module for NearCam and for NEARES that will get plugged into, in particular, Dolpho, but also into other Python packages. Because the pipeline for JWST is only going to produce aperture photometry, so this is an essential part of resolved star studies that we're going to deliver. And then we'll also create interactive data reduction demos to show you how to take your data from the images to a final PSF point source catalog. And then we're going to have a workshop prior to Cycle 2 to help you design your Cycle 2 proposals for resolved stellar populations. And this program is using only NearCam and NEARES. These are the two workhorses for imaging resolved populations. We'll be using NEARES in parallel, and this is actually the only NEARES imaging proposal that is in the ERS program. And here are our targets. We've got a globular cluster, an ultra-faint dwarf, and a local group star-forming dwarf galaxy. And these may change depending on the launch, but they'll stay in these same categories. And for all of these targets, and for both NearCam and NEARES, we'll be using 0.9 and 1.5 micron filters, since these are sort of the primary stellar population filters. But then, since with NearCam we get 2 long wavelength filters for free, we're doing 2 different ones for each target to study different aspects of the science. And that's it. So if you have questions, I'll stay there.
Hi, I'm Sylvain Veilleux from the University of Maryland. Our program is called Q3D, which stands for Quasar in 3 dimension, and basically consists of imaging spectroscopy of quasar hosts with JWST. We're particularly interested in the impact of accreting supermassive black holes on the galaxy evolution. And it's been argued for many years that the so-called quasar feedback is responsible for the steep decline of the mass function of galaxies, and also the correlation between black hole mass and properties of the bulge. And it would be nice to test it observationally, so that's the plan. And we argue that imaging spectroscopy is the best way to do this. And so we put together a team that is all listed here, the complete team of experts in quasar science, but also in integral field spectroscopy. The team is led by Dominika Ulisarek, Nadia Zamkaska, and myself. So we have 3 targets. All 3 are powerful quasar with known galaxy-wide outflows, and by design, they are chosen to have a broad range of redshift, as shown here, from redshift 0.4 to redshift of 3, but also a range of obscuration, range of luminosity as well, and then finally range of quasar to galaxy contrast. to really fully test JWST. We're planning to use the IFU spectrograph on NIRSPEC and MIRI, and then we're going to use a number of spectral elements to get many of the critical strong line diagnostics for ionized gas, for molecular gas, and also for a star formation indicator like PA. So this diagram on the lower right indicates sort of the range of wavelength that we're going to be covering. For the lowest targets, the easiest one, which is at the top here, we're going to be covering continuously from 1.6 micron to 28 microns. So we're going to get a lot of information. The critical aspect of this program, I would argue, is our software. We're going to be using what we call IFS FIT, which is a PSF decomposition and spectral analysis package that we have tested and used for ground-based data, optical and near-infrared ground-based data, and that we're going to be modifying for JWST data. Some of the details are in this paper by Rubke in 2017 that we published last year. So the plan is to make this software available to the community. We're going to learn a lot about information from this software as well, which we'll make available to the community. We think this software is going to be critically important not only for Quasar study, but if you have a program that has a bright PSF in its IFU observation, I think this software will really help you to get the data out and be able to remove the PSF, the bright PSF. So, thank you.
Hi, my name is Merida Batiste. I am a part of the team led by Misty Bentz at Georgia State to look at the nuclear dynamics of the nearby CFIT NGC 4151 using near-spec integral field spectroscopy. So in comparison, we're a fairly compact project and have a fairly small team. So we also have Monica Valuri at the University of Michigan, Caroline Roberts at Georgia State, Christopher Onken at the Australian National University, and Eugene Vasiliev at Oxford University. So the primary science goal for this program is to measure the mass of the supermassive black hole in NGC 4151 using stellar dynamical modeling. This is a particularly interesting target for this because NGC 4151 is one of the very few nearby broadline AGNs that has a black hole mass from reverberation mapping, which is also close enough that we can resolve the sphere of influence of the black hole and therefore use stellar dynamical modeling to also get a black hole mass. These methods are both very commonly used in the literature, but there are so few galaxies for which you can use both methods at the same time that we don't yet know whether they give consistent results. So this is a target where we can do that. Really the power of our observations for the community is that we also have observations of the nuclear dynamics for this galaxy using Gemini NIFS, which is an AO-assisted integral field unit, which is extremely similar to the near-spec IFU. And so that will provide a direct comparison for the community to see what kind of benefits you can get using the near-spec IFU in comparison to Gemini NIFS. So in addition to the stellar dynamical modeling results, so the black hole mass that we're going to get, we'll characterize the PSF and compare that with what you get with an AO-assisted ground-based instrument that's similar, because when you use AO, you can get this sort of quite compact central AGN, but you also get a seeing limited halo, and that's something that will go away with JWST. We'll be able to probe how close into the center of the galaxy we can really get good stellar signatures, so really sort of how well we can get the AGN compacted and how close into the center we can get good dynamics. We'll provide both gas and stellar kinematics maps, and in the process of doing that, we will be able to see how well we can characterize the line-of-sight velocity distribution and really how well we can characterize the higher order moments of the line-of-sight velocity distribution. And we'll provide maps for all of those. We will also, as part of this program, be observing 4 late-type stellar velocity template stars, and we'll be able to provide that to the community as a small initial library of stellar templates to be able to use for that.
thanks. I'd like to also start, just like Mark did, by thanking Ken. I think this is incredibly exciting for us. It was a great idea to prime the pump for JWST. It's so important because the opportunity is so great, and the increase in the resolution and the sensitivity is so much compared to previous missions, that you really need a program like this to allow the community to understand what you're going to get from this telescope. And it was a great idea, and thank you for doing that. So I'd like to tell you about our program, which is called a JWST Study of the Starburst AGN Connection in Merging Luminous Infrared Galaxies. This may have been the only proposal where I didn't come up with a catchy acronym, and I apologize for that. Here's a list of all the people in our proposal. We have a large group, many people from the GOALS project. If you want to find out more about GOALS, you can go to the GOALS website. I'm sorry I didn't put that up there, but you can easily find it or talk to us after. 18 institutions, more than 20 COIs, and 8 countries. So I tried to summarize our program in this one slide here. We're looking at 4 objects in the nearby universe at low redshift, all selected from the GOALS survey to cover a range of properties with both starburst nuclei, AGN nuclei, and starburst and AGN and nuclei. And primarily our observations are targeting the MIRI IFU spectroscopy of the nuclei of the galaxies, with a resolution of 50 to 100 parsecs in every single source, covering the central few kiloparsecs, near-spec IFU spectroscopy, and MIRI and near cam imaging of each galaxy, and also some subarray rapid readout modes for some of the bright nuclei, so we'll be able to test the saturation and recovering from saturation. For us, the most important part of this project is that it's going to produce a high-resolution dynamic map with a multi-phase ISM in nearby rapidly evolving galaxies, such as these merging luminous infrared galaxies. We're going to get JWST images, spectral cubes. We're going to make 1D fitted spectra. We're going to produce software modified from the software that we use for Spitzer, which is called Cafe, to fit the mid-infrared spectra. We're going to provide the fits for all the spectral cubes, and also the software spectral package is going to allow us to make 2D spectral maps and all the key diagnostic features, pH features, the emission line features, the fine structure lines. And anyone that has done Spitzer spectroscopy knows that we've been studying these galaxies for a long time with Spitzer. This is an enormous leap. 5 to 10 times the spectral resolution, 50 times the sensitivity. It's almost hard to understand what we're going to see in these galaxies. We're so excited about that. And I think that an important part of this program is to understand what we're going to see and to lay the groundwork for cycle 2 proposals. And so I'm showing a couple of the sources down there. There's NGC 3256, which is a 2 nuclei merging starburst galaxy, and NGC 7469. So many of the people in the audience know these sources, have studied these sources in their career. 7469 is a nearby Seaford with a starburst ring. And I've listed the 4 sources we're going to do there. There's a typo. It's IR 08572 plus 3915, not minus 3915. It's one of the most obscured infrared galaxies in the local universe with a powerful outflow. And VV114, a lot of you know that source as well. It has an incredibly distinct pattern in the east and west objects. One is highly obscured. All the UV light comes from one source. All the infrared light comes from the other source, has a powerful outflow as well. So these are well-studied objects, specifically in the infrared and with Spitzer, but with this tremendous leap, we're going to be able to really address and understand the starburst AGN connection in local galaxies. And one thing that GOALS brings to the table and our project brings to the community in particular is a wealth of ancillary data, and we're going to provide this as part of our ERS program to the community, and that data will consist of HST, deep imaging, Spitzer, Herschel, JBLA, and ALMA data, and we're going to provide all those images and data cubes to the community as part of this program, along with a software spectral fitting package. Thank you.
All right, floor is open for questions.
So why didn't we use what as well? This, just because we were really focusing on doing the near-infrared 0.9 and 1.5 micron star formation histories and IMF studies, but then because we can use the long wavelength filters with NIRCam, we'll also be able to study things like evolved stars and young stellar objects and map extinction, things like that. So it was sort of it's actually a bonus for the program. It wasn't meant to be one of the main focuses, but you can demonstrate sort of, if you're focusing on just doing resolved stellar populations and doing a star formation history, you can also do all this other extra great stuff for free in the same system with the long wavelength NIRCam portion. Probably not, because the wavelengths aren't long enough for that. We'll have to follow up with Mary later. But we will be able to identify all of the evolved stars, all the dust-producing stars. Whether or not we can measure their dust production rate is another question with this data. So.
Okay. While people think, I want to remind everyone that these slide sets will be available on the AAAS events page of jwst.stsci.edu. So I know some of these quad charts are tight. You can go look at them there.
So while the slide is up, so what is nearest rate to the table with the 90, 150 pixels are much bigger?
It is, but it's actually more sensitive. And it's going to be pointed at the halos of these galaxies. So it'll bring this sort of extra dimension to these studies, where we can study not only the core of the system, but what's going on with the stellar populations in the halo too, and actually a little bit more depth. Parallel imaging, right. So we'll be out where it's less crowded, so the larger pixels don't matter as much. But we'll be providing an analysis of crowding and sensitivity and all these things with PSF photometry. So you'll be able to plan your cycle 2 proposals. Yeah.
So I was just going to follow on from Margaret's question to point out that one of the ways to use the frontier field of JST is as a seed for other programs. You should, if there's something you think is missing, obviously these guys can apply for everything to cover the science that they're after. These can be seeds for cycle 1 programs. There's no reason why you need to follow up with viewing observations in cycle 2. You can propose for that in cycle 1. If there's something obvious here that you think needs to be added to these programs, apply in cycle 1.
Absolutely, yeah.
I mean, that's a really good point, because you can see in our program, for example, I mean, the spectroscopy is very important for us, but we could only target the nuclei in our sources. Our images are going to cover the entire galaxies, but we're only going to get the MIRI IFU and the NIRSPEC IFU data in the central few KPC. And there's many more things that can be done in these objects. It's an introduction, and it's to get people excited about it and to show what's happening right around nuclei, but there's a lot more that can be done.
All right, you guys have 1 minute left while I go back to the different other slides. Oh, I saw someone stand up. I thought he was going for the mic. Okay. We'll move on now to astrochemistry and the ISM.
All right, so my name is Ryan Lau. I am the PI of the WR Dusters team. I apologize for not putting the names of the people on our team. I thought it was going to take up too much of the screen. But some of the people in the audience who have done a lot of work are Matt Hankins, Ted Gull, and I think I also saw Betsy around here too, Betsy Mills. All right, so to sum it up, essentially the main focus of our program is to answer the question if you can detect really faint stuff around something that's really bright, and what does that look like? Hence our title here, Establishing Extreme Dynamic Range with JWST. The specific target that we're looking at is called WR140. It's a dusty Wolf-Rayet star. And one of the reasons why these types of stars are interesting is that it turns out a lot of massive stars have binary companions that are close by. In fact, most of them should be interacting with their companion. So there's a question of whether or not most stars go through this phase and produce potentially significant amounts of dust. And so these systems will also go through this phase before they explode as supernovae. So perhaps these types of stars can supplement the dust that's required to make up the dust budget in early universe galaxies. So what we're trying to do is we're using MIRI, the mid-resolution spectrograph, to get 5 to 28 microns IFU spectra of this target right here. You can also see that the size of it fits nicely in the MRS and also the nearest fields of view. So that's our other goal, is to use aperture masking interferometry to get really high spatial resolution observations of this particular system. And the goal of these two programs is to look, or these two observations, is to study how dust actually forms in these dusty Wolf-Rayet binaries, and also to look at the chemistry, which is key. That's what JWST essentially allows us to do. You can observe this from the ground, but it's very difficult to get spectra of this dust. And we can also get dust that formed at previous epochs, so you can see how that dust is evolving over time and get an idea of what integrates into the ISM. All right, so as I mentioned, our goal is to see if we can detect really faint stuff around something really bright that tends to create a lot of issues in mid-infrared observations. So we want to provide tools, software tools, where we can mitigate these artifacts in the infrared. So using techniques from Forecast and SOFIA or with Spitzer to try to mitigate these same detector artifacts that you might see with, or that you will see in MIRI. So as far as engaging the community, attending meetings, interacting on web-based forums, and also engaging with theorists to get them involved with colliding wind models to try to predict, or to try to actually figure out how you form dust like this. One other idea that was also suggested for our program is that we have this interesting idea of making a 360 video where you can actually put yourself at one of these stars and see how this dust, this shock cone flows out. So that could be kind of cool. So I'll just leave this slide up for a little bit. These are essentially just summarizing the technical and our science goals that we're trying to do with both MIRI and NIRIS. Okay. Thanks.
So hi, I'm Ted Bergen, representing our team that's going to talk about or observe radiative feedback from massive stars using multi-band imaging and spectroscopic mosaics. I want to represent my excellent PI team of Olivier Byrne, Emily Hubbard, and Els Peters. What are we doing? If you think about it, any gas surface in any galaxy is essentially a photodissociation region. It's exposed to ultraviolet radiation. And many of the spectra that James Webb will take will be dominated by the emission lines from this dense irradiated gas nearby, particularly surrounding massive stars. So we wish to obtain 1 to 28.5 spectroscopic maps of one of the template PDRs in the galaxy to help us all understand what we're going to see. What you see there is the Orion bar PDR, and on the far right there, or left for me, you can see the green area is the H2 region, getting into blue where it's the ionized gas, heading where you're getting to the dense gas, and then the neutral gas is in black, and then the molecular region. And with James Webb, we will be able to resolve each and all of these regions. So what are we going to do? It's near spec IFU spectroscopy, about a 10 arc second field. And MIRI IFU spectroscopy, again, over the same field by and large, and supplemented by both NIRCam and MIRI imaging over a much larger field. These spectra will be dominated by lines of both dust features, PAHs, and molecular and atomic emission lines that will change from point to point. And so we will be providing products to show you, the rich spectra, what features do you see down to the weakest features. But also the team is really engaged and interested in providing useful tools to the committee. So there's one that's called PIPA-FIT, which will decompose the spectra from the dust features and the gas features and provide maps to go along with that, a line catalog, a fitting tool for H2 emission lines so you can plug them in and get physical properties such as the gas temperature and the H2 column density, a interface with one of the best photo dissociation region models that exists to date for you to generate massive grids of models that anyone here that sees these emission lines in their data can then extract salient physical properties from that. And the team in particular are incredible PAH experts. So they will link to the best PA database that are out there, and it'll allow you to actually use the PA bands as well. So lots of information that will come to you from this program. Thank you.
So my name is Klaus Pontoppidan. I'm representing the ICE team. I'm a team member. It's PI'd by Melissa McClure, Edwin Bogart, and Harold Linnets, and there's a large multinational team behind this. The key objective of this program is to study interstellar ices with JWST and to demonstrate that JWST will be a premier facility for studying interstellar ices. Why is that important? Well, in dense dark clouds, you have enormous amounts of ices, in particular of water, and this is in fact maybe where most of the water in the universe resides, as ice mantles and dust grains. And they play a critical part in creating and delivering water and other volatiles that end up on habitable planets, so it's important to understand this step of interstellar chemistry. So this program aims to observe ices with many different modes, in part to establish which observing modes are best for observing ices. So we'll be using 3 different instruments, NIRCam, NIRSPEC, and MIRI, and various modes with them, and to try to really highlight the strengths of these different modes. We'll be delivering, of course, representative spectra of ices in various stages of star formation, routines that enhances the pipeline, in particular extraction of spectra using the slitless modes in crowded fields. But I think one of the most important things that this team will provide is public laboratory ice database. So we have premier lab facilities that can create spectroscopy of ice analogs that you can use for comparison with ice observations in general with JWST. One of the things that we are really looking forward to doing is to do ice mapping toward background stars. Right? So how do you observe ices in dark clouds? You do that by absorption spectroscopy. And so typically you would have some source either behind the cloud or embedded in the cloud. If it's behind the cloud, it's some star far away in the galaxy. And in the past, those have been looked at one at a time. Taking up a lot of time, for example, with Spitzer. Now, with JWST and using the NIRCam slitless mode, for example, we can obtain spectra of many stars, more than 100 here, and you can show this is the field we have in the chameleon star-forming region, and the blue dots there, they'll show the positions of known background stars. And so essentially you get a column density of all different ice species along the line of sight toward each one of those dots, and you can use those to reconstruct a map of the region and understand where the ices form, when they form, at which depths into the clouds they form, and get a really, finally, a full or a much more complete understanding of the chemistry that formed the ices. And that's an example of an ice absorption spectrum here toward a background star in this field here. In addition to that, another highlight of this is that we'll do some pointed observations of a protostar, of an edge-on protoplanetary disk, as well as of 2 background stars with some of the highest known column densities of dust, the highest known extinctions up to 100 magnitudes. And we'll use those, so very sensitive fixed-slit near-spec observations toward those to search for the presence of very rare species, in particular complex organic molecules. And this was not at all possible before. The sensitivity of JWST is what really allows that to be possible. So we're very excited about that. Thank you.
All right, these are now open for questions.
Well, it's just a clarification. So you expect to get about 100 ice spectra in this ERS program?
Yes. So if we go back here, right, so that's the near-cam field of view, and so we use the slitless mode, that all gets dispersed. And so these are just the known background stars that have been seen with Spitzer. We actually expect JWST to be sensitive enough, you'll pick up some stars that weren't even seen with Spitzer, and so you can count the dots that are there. We won't get the full spectrum in each one of those, but that gets into some detail, but let's say about 100.
So Klaus, why are you not using your spec MSA?
Well, we have to do pre-imaging for that, right? So when you use near-spec MSA, you need to have very good astrometry for all your sources. And so we have to do pre-imaging for that, and so that's hard to do in an ERS. I think as a follow-up program to this, it could very likely be a near-spec MSA proposal to try and do the same thing and evaluate what's better. Here we're trying it with the slitless mode, because that's just point and shoot.
All right, last call. All right. Thanks, guys. And I guess now we have our planets folks come on up. I'll use this opportunity to point out that there is one group missing tonight, and that is the ERS that is going to look at Jupiter. So that is Imke de Potter at UC Berkeley, and she's not here tonight because she's planetary and this is AAS. So.
Thanks, Bonnie. Okay, my name is Kevin Stevenson. I'm here on behalf of not only the transiting exoplanet community that submitted the proposal, but hopefully the entire exoplanet community itself. And I'll talk a little bit more about that at the end. This really was a community effort on behalf of the Transiting Exoplanet group. We had over 100 investigators and collaborators on this program. It was headed up by Natalie Battaglia as PI, and Jacob Bean and myself were both co-PIs. Now, the structure of our organization was such that we needed a science council in order to really bring together the entire community and listen to all the feedback that they had. So that was chaired by David Singh, and we also had 4 working groups: Transmission, MIRI, Bright Star, and a data challenge working group that really was meant to address all of the concerns and the science products that we needed to produce for such a program. We had experienced a good balance between both expertise and geography within our group, and we had a strong female contingent within the leadership roles. Let me take a minute to talk about the observing program itself. We received a total of 78.1 hours. That doesn't seem to be showing up there. This was the largest program of all of the ERS programs awarded time. It was divided into 3 groups. The panchromatic transmission program was the first group, nominally looking at WASP 79b, which is a hot Jupiter planet on a short orbital period. The entire purpose of the observation is to obtain transmission spectroscopy observations. This is when the planet crosses in front of the star, using multiple modes. So we have 2 GRISMs with the near spec, one near a SOS observation, and also a NIRCam F322 double wide filter observation. And really what that allows us to do is obtain transmission spectra from 0.6 to 5 microns over the 3 instruments, and allow us to evaluate the performance of each of these instrument modes against each other, which is the first time that we'll be able to do this for transit spectroscopy. This will allow us to understand the instrument systematics and gauge which one produces the most reliable results. The second program is the MIRI phase curve program, nominally looking at WASP 43b. This is a very short orbital period hot Jupiter, about 19.5 hours to make one full rotation. We'll observe the entire phase curve observation of that planet, starting with secondary eclipse, moving through transit, and then finishing off after the second secondary eclipse. And really, this will allow us to test the long-term stability of the MIRI LRS instrument, as well as serve as a proof of concept for future phase curves observations, which produce a significant amount of science based off of a single observation. The third program is a bright star planet observation. Nominally, we've selected WASP 18b, another hot Jupiter. This one is really instrumental in terms of assessing the noise floor of these instruments, in particular the near IR instruments. It'll allow us to really obtain the information that we need to do repeated observations of these planets and really push towards those small exoplanet observations. All three of our targets are visible during the 5-month nominal observation period for the ERS program. And we also have the data products and data challenge. We have science enabling products where we will deliver Jupyter notebooks so that people can see how we've analyzed all of our data step by step through that process. We will have data challenges, a two-step or two-phase data challenge, the first of which uses simulated data, and the second of which will actually use real ERS data, allowing anyone to get involved and understand the data from the very beginning. The last point that I want to make is that we are open to the entire transiting exoplanet community, so if you're interested in getting involved with this program, even if you weren't on the program itself, feel free to reach out to myself, Jacob Bean, or Natalie Battaglia. Thank you.
Hi everyone, I'm Elodie Choquet, I'm a double fellow at JPL and Caltech, and I'm going to present you the second ERS program about exoplanets and last of this session. So this program is about high contrast imaging of exoplanets and exoplanetary systems. It is led by Sasha Hinckley from University of Exeter with as co-PI Andy Skimmer from UC Santa Cruz and Bess Biller from University of Edinburgh. So this is also a large effort from the community, and we have 120 co-Is who support and contributed to the development of this program. So it's a 39-hour program in which we will characterize the capacities of JWST to study planet and planet formation through direct imaging and spectroscopy. So as part of this program, we will obtain for the first time a complete spectrum of large separation exoplanets for the full luminous spectral range from 2 to 28 microns. We will also obtain images of a debris disk out to 15 microns, so probing both the scattered light regime and thermal emission regime. And so on these images you can see a simulation of one of our targets with the chronographic modes of NIRCam and MIRI, which show how well we expect the Webb telescope to image a 17 megayear-old exoplanet of 6 Jupiter masses with these two instruments and their chronographic modes. And so we really designed this program to use all possible modes that provide direct imaging with all 4 instruments of JWST. And our goal is to produce representative data sets to deliver back to you, to the community. So we organized our program in 4 observing work packages and 1 theory work package. The first one will consist in obtaining chronographic images of a known exoplanet with the NIRCam and MIRI chronograph in order to evaluate the chronographic performance of this instrument and define their contrast limits. Then, in the second work package, we will obtain chronographic images of a well-studied debris disk, also with NIRCam and MIRI chronographic modes. data will image this disk on and off the water ice band to characterize the water ice content in the system. In the third work package, we will obtain a full spectrum of the wide separation exoplanet in the near-infrared with the near-spec IFU, and in the mid-infrared from 5 to 28 microns with MIRI MRS mode. And with this dataset, we will analyze molecular abundances and silicate clouds in this exoplanet. And finally, we will also obtain deep aperture masking datasets with the AMI mode of NIRIS, with which we will evaluate the systematic phase error of this mode that defines the contrast limit for aperture masking interferometry. And finally, I will just leave you with our team member list, which includes 40 COIs and 80 science collaborators all over the world. Thank you.
Okay, so these two presenters are available for questions now.
Kevin, I have a question for you. What are you going to do with the short wavelength arm with your television?
For cycle 1, the short arm of the NIRCam mode will only be available for imaging, not for DHS. So what we'll do is we'll use we'll disperse the light so that it is using, I guess, the WLP8 filter, which essentially allows us to monitor the position of the centroid of the star and then measure the spectrum with the long wavelength arm, and that allows us to remove position-dependent systematics.
Question for coronary technology. Are you using the small grid dither technique to maximize the PSF subtraction?
Yes, exactly. So one of our goals is really to try different PSF subtraction techniques. So for the coronagraphic imaging of the planet and the disk, we are going to use a reference star, the small grid dither, and 2 rolls of the telescope to analyze the performances of every possible PSF subtraction techniques. And we will give you that back to the community.
Okay. Last chance. Okay. Thanks, guys. Okay. And a last big round of applause for all of our ERS presenters, please. Okay. Our last presentation of the evening is JWST User Tools and Resources by the project scientist at the Institute, Nicole Lewis.
Well, thanks to everyone who stayed, even after the food ran out. Feedback there. There we go. Well, I'm going to give you a little guidance, sort of lay the roadmap for you now that you've had these seeds planted in your heads about all of the proposals you can be doing to complement these ERS programs. But first, I just want to start with just overviewing what we actually do at Space Telescope Science Institute for JWST. Many of you, of course, are familiar with us from operations of Hubble, and of course are probably most familiar with this part of the process right here, which is proposal preparation and selection and science planning. Of course, also, many of you are familiar with interacting with us with the MAST archive as well, but there's a whole heck of a lot of stuff that we're working on in between here and there for JWST, including the Flight Operations Subsystem. So this is a little snapshot of the Mission Operations Center being housed at the Institute. We also do a large amount of science community and public outreach, which many of you are familiar with. So let's just lay the landscape for Cycle 1 Science with JWST. And so here's your science timeline for Cycle 1. We are, of course, here at the beginning of 2018. The Director's Discretionary Early Science Program and the Guaranteed Time Observers programs have been closed. Those programs have more or less been finalized, and all of the information about those programs are basically available to you now. They're publicly available through our website and our basically proposal information tool. Right now we're in the midst, of course, of the General Observers Program. So reminder, of course, the Cycle 1 deadline is April 6th at 8 p.m. James was kind enough to highlight this supplemental General Observer call. So this is meant to capture all that great science that's going to happen in between when you submit your proposal here and whenever launches. So this supplemental call is going to be strongly influenced by input from you, the users, through the JSTUC, and will basically occur right here straddling launch when we issue the call and then accept those proposals so that we can rapidly fold them into the regular Cycle 1 science observations. So a little bit more about the GEO call that's now out. Again, it's been released and they're due on April 6th. We expect the Time Allocation Committee will meet in June 2018 and the selections will be announced in July of 2018. Here's what we're looking at currently in terms of program categories. The first cycle will be heavily weighted towards these sort of small programs, so less than 25 hours. This is, of course, subject to adjustments by the Time Allocation Committee. One thing I really want to highlight for folks is that there's more than just proposing for these observations. There's calibration programs, there's long-term proposals, treasury, surveys, there's theory programs, data science, software development, and archival programs. The ERS programs enable you to propose for archival programs that are related to those data because they will be, of course, available to you as soon as they're taken. So keep that in mind, and I encourage everyone to read up about these programs because there are new opportunities that folks can take advantage of. Now, the full details of the General Observer call can be found on what's called JDocs, and you've probably heard that word bantered around a little bit now, but let me explain to you what JDocs is. And that's just the JWST user documentation that we lovingly refer to as JDocs. It's housed here at jwst-docs.stsci.edu. This is really a new paradigm for JWST user documentation. I mean, I know all of us really loved lugging around those 100-page PDFs when we're trying to plan our proposals, but now basically we have this philosophy that every page is page one. So they are short, self-contained articles that are heavily hyperlinked to each other, so you can kind of go through and find what you need to find in order to plan your proposal. Sort of like Wikipedia, but it's not a wiki. JDocs has multiple conceptual spaces, so there's background articles, planning cookbooks, science policy area, which is where you're going to find your calls for proposals, engineering specs, etc. I want to highlight some recent updates, and that includes science use cases for all 4 JWST instruments with, that are designed to walk users through the steps for crafting a JWST proposal. There are help videos to assist users with various tools, sort of like getting started with JWST APT or Astronomer Proposal Tool. Those you can find through JDocs, and they're hosted on YouTube on the JWST Observers channel. You can also find information about new tools such as the Backgrounds tool, which I'm going to talk about briefly, the NearSpec Observation Visibility tool, and the NearSpec MSA Spectral Visualization tool. So you're going to see a lot of sort of web links throughout this presentation, but the only one you really need to remember is this one. Hopefully we've constructed the website in such a way that you can find what you're looking for. In fact, I was just here in the documentation area right here looking at JDocs, and now I want to highlight actually this news and events area where we have a substantial amount of information about all of the workshops that have been held, as Eric was kind enough to point out. There's been basically more than a dozen in-person proposal planning workshops that have been held. There's also been about 24 of these community lectures / webinar series. All the materials and all of the recordings from all of those, both the workshops and the webinars, are actually online. You can go and sort of virtually participate in anything that has happened over the past basically 2 years. That includes slides, and if the workshop had hands-on activities, those workbooks and such are there as well. So you can go and look at these events, go through, find the training material, find the recordings. The recordings are also all hosted on the JWST Observer YouTube channel, so I encourage folks to look that up. The other thing I want to highlight is our news area. This is called the JWST Observer News. This is where the first releases of information happen, and then they are quickly then tweeted and posted on Facebook. So to stay up to date, I suggest that folks really subscribe to on Twitter or Facebook. But if you don't tweet or go on Facebook, it's okay. We'll keep you in the loop via the JWST Observer News Roundup, and it's delivered to your inbox. So basically, we wrap everything up, send it to you, and then you can go through, read them at your leisure, and follow the links through to the various information. You can manage your subscriptions to JWST Observer News through this profile.stsci.edu. All right. So let me highlight a little bit about a lot of the tools that you're going to be needing to plan your awesome Cycle 1 proposals. And we have basically a JWST Observer toolbox set up that's, of course, housed here, and you can easily find it again from that top menu. It includes a variety of software tools. It also includes simulated data and guides to assist users in understanding the capabilities of JWST. As many people have said throughout today, JWST is complex and there are a lot of modes, so we're trying to help you to understand where to go, what might be your best options. I, of course, want to highlight two of the tools that most folks will first interact with, and that's the JWST Exposure Time Calculator. So this is, again, available. You can find it through the website. This is done online, hosted on Amazon Web Services, and is really, really a great way to try to understand what kind of signal-to-noise ratios you're going to get for various instruments and modes. And once you kind of have a good idea of what you want to observe and if it's doable, here we have the Astronomer Proposals tool, which looks a lot like what folks are familiar with from HST, and it provides various templates that help to guide you in the selection for various instruments and their modes. I wanted to briefly highlight the JWST Observer Tool's newest addition, and that's the Backgrounds tool. Sorry, there's a box missing here, but that's all right. We'll fix it later. So basically, it's hosted on GitHub. Again, Python. We're really about open source here. And what it does is it allows you to put in an RAN deck and then find basically what the background level is at various wavelengths at different days in the year. So that if your program is really background limited, that you can find those areas where you have the days where you have the lowest levels of background and put that into as constraints in your proposal. So check that out, download it, play with it. There are a lot of tools, and it's kind of overwhelming at times. It's overwhelming for me, but I want to reassure you that we're here to help. Okay. The JWST Help Desk is a sort of a new paradigm as well. So no longer should you email help@stsci.edu, but go here. And what this does is it's a portal that allows you to come in and sort of self-direct the areas you want to reach, whether it's the instruments, maybe you're really, really interested in the pipeline, say, or maybe math services. There are new cards coming soon. We're updating them as we get input from you about the areas that are of particular interest. The best part here is that as we collect this information, it allows us to grow our knowledge base so that folks can go in and maybe see frequently asked questions and get that information right away. All right, so here we are at the AAS, but I encourage you to stop by both the Space Telescope and the NASA JWST booths to talk to us. A lot of us are going to be around. You can pick up a JWST pocket guide. At the STSCI booth, we're going to have APT and ETC demonstrations. And I want to highlight here this time tap here, which allows us to schedule one-on-one sessions through our Ask an Expert. So if you have a burning question and you'd like to talk to an expert about, say, Miri photometry, see if you can grab someone to have that conversation with. I also want to highlight that there is an opportunity to participate in our virtual and augmented reality experiences at the STSCI booth, including the newest, which is basically come experience planet formation. So if you like to do a little VR fly through this protoplanetary disk, come by the STSAI booth and check it out. And I just want to highlight finally that everything that you've heard today and seen has been recorded. We're there in the back. It will be posted online as soon as it's ready. All the slides will also be posted online. And again, you can find it through this news and events area under the AAS meeting here at News and Events. I also encourage you to subscribe today to our YouTube, Twitter, and Facebook feeds for the Observer channels. This will be a great way for you to get the latest information about JWST's capabilities and any new tools, et cetera, that come online. I think with that, we are now at the point for open mic time. Are there any questions specific? Just open mic time? All right.
Is the expectation that they'll be working with members of the ERS teams and they're going to work with your data, or can they just be completely independent and just go on?
Independent? Either.
So I'm Neil Reed. I'm the, what am I? The Associate Director for Science, I guess, at Space Telescope. So anyway, so we've been talking about this. There are complications in the launch slip. We do intend to get funding to the ERS teams as fast as possible. We're not going to hold up the funding until the data are taken. That would not make any sense at all. There will be, we're going to be iterating with the project. You have to figure out where to take the money from and so on. So it's complicated because there's now just the way things have worked out. But we will get the money to the ERS teams as fast as possible. We will also try to get, in advance of that, some kind of certification to the ERS teams so that you can go out and put out adverts. So you can tell, the ERS teams can tell their universities, we will be getting money. And the university will believe that and say, yes, you can now put an ad out. So you can actually start to hire people who will come in when the money arrives. But the exact details for that remain to be defined exactly. But you have our good intentions.
I just wanted to put in a pitch regarding the archive at Space Telescope Science Institute, since there was a question about pipeline functionality. I just wanted to say that the data management system has indeed been tested with their cryograph data, and as data are made available, and such as the early release science, all of the uncalibrated and calibrated products will be available through MAST, the MAST interface, the portal, which has a demo here at the booth, the STSCI booth. We will also make higher level products available. We have basic functionality in terms of dithers and mosaics. And since most people are familiar with high-level science products through HST, there will be similar high-level science products delivered to JWST by such teams. So these are contributed products by the community, and they will also be put into the master archive and will be searchable through the portal. So all products, as they are, depending on their proprietary period, these are not proprietary, will be made available as soon as they're processed through automatic pipeline processing.
Thank you to all of our presenters one more time. And thank you to all of you for coming tonight and staying for 2 hours and asking good questions, and go enjoy your evening.